Okay. How this caches will help to improve the performance of a processor. Because why these caches are needed or how these caches works, let's see. For the program locality, for any program, we know that there are two now the program locality concepts are there. That is the memory hierarchy that exploits program locality. That is, the programs tend to the reference parts of their address spaces that are local in time and space. So, local in time and space means there are two times. One is temporal locality, that is, recently referenced addresses are likely to be referenced again and again, that is, the reusing. Second one is spatial locality. If an address is referenced, then the nearby addresses are likely to be referenced soon. So that is spatial locality. So programs that don't exploit the locality that won't benefit from these caches, like machine learning applications, or typically have low data locality. So these programs are called the streaming programs. So these programs are called the steering programs, means they are the main focus of today's system research. But in this, let us see by using the hierarchy of this program locality, how it helps to place the recently referenced data or recently accessed memory into the cache, so that that will improve the what you call the performance of the CPU. So let us see that. We have a program. That program is compiled. So compiler generated the instructions. So for that program, it generated 8 instructions. So these 8 instructions, assume they are ready for execution in the pipeline. So first, let us see if there is no cache memory. So without cache memory, how it is accessed? This program that will be loaded inside this memory unit. So then the CPU at the program counter issues the address of these instructions in a sequence for execution. So in this 8 instructions, let us closely observe instruction at location 4 and instruction at location 8. This is a memory instruction that states that fetch the value A from the memory and load into R1 register. So CPU, that means inside the CPU we are having program counter, which we discussed in the instruction fetching stage of pipeline data path design. So that issues the address of the operand or the value A, that is at location 4 in the memory. So location 4 means it is the 4th block in the memory. So that searches in the memory and it finds, once this program is loaded, this instruction loaded in the memory, this block of memory is located. Then this block of memory, this value A is fetched and load into the register. So that operation happens inside the CPU. So this A is fetched and load into R1 register, where register is inside the CPU. So what is the latency means? The data is, the value A is accessing from the memory, that is far away from the ALU unit, so are the registers, so its latency is 100 nanoseconds, which we observed in the previous slide. So without this cache, to execute the memory instruction move R1, move the value A into R1 register, that takes 100 nanoseconds. If you closely look at the eighth instruction, the instruction at eighth location, that is also accessing the same value A, but loading into R2 registers, second time. So again, the value A is requested, and that is will be identified and send it back to the CPU. So again, its execution takes 100 nanoseconds in pipeline. So the total execution time for these two memory instructions, which are accessing this the data value from the same block of memory, is taking 200 nanoseconds. So then, after designed the caches and placing the cache memory, or the memory hierarchy, like L1 cache, L2 cache, L3 cache, which are L1 and L2 on the chip, and L3 that is surrounding the core. Then how it is giving the difference? So in this example, let us assume that the L2 cache is taken into account. And then let us see to execute these two instructions, which are moving the value A into different registers. So L2 cache, that is inside the CPU chip, then how it helps to increase the performance. So first, the requested block of memory will search inside the cache. If it is not there, then searches in the next level of memory, that is memory unit. And it locates the block of memory where the piece of data is available, that is A. Then this block of memory, entire block, not the say piece of data, that is A, is transferred back. Entire block is fetching from the memory, and one copy of this block of memory hold in the cache. And the piece of data A is used to move into R1 register inside the pipeline execution. So what is the total execution time for this particular operation? Is it is accessing from the main memory, taking 100 nanoseconds. So while executing the eighth instruction, again, same piece of value, that is A, is moving into R2 registers. So for the eighth instruction, it first searches into the cache memory, and that piece of data is readily available. So that piece of data transfer to the CPU. So we are assuming here this is a L2 cache. So then the latency time is 10 nanoseconds. So that executed in 10 nanoseconds. So with cache, these two memory instructions executed in 110 nanoseconds. So if there is no cache, it takes more execution time if there is a cache that is taking less execution time. Less execution time means the performance of processor is increased. So this motivates to design the cache memories. So that is what why these caches are work means they improve the performance. So from this example,